By the middle of the 19th century, the night sky had been mapped in exquisite detail, and yet its true depth had remained wholly unmeasured. For nearly all of recorded human history, the stars had been treated as ornaments fixed to a distant surface, arranged into patterns that carried the weight of prophecy and myth, but never the burden of scale. That assumption had persisted not because earlier thinkers had lacked curiosity, but because the instruments available to them had never been capable of proving the sky to be anything other than what it appeared to be, which was a ceiling. To look back from where we now stand is to see how quietly the transformation began. There was no single announcement, no thunderous overturning of belief. There was only a patient astronomer in a small observatory on the eastern edge of Prussia, watching a faint star for months on end, and eventually arriving at a number that no one before him had ever possessed. That number, when it was finally published, redrew the boundary of the knowable universe. And every era that followed, including the one we live in now, has been an extension of the geometry he first established. The story of how humanity came to understand the age and expansion of the cosmos is, in truth, the story of the telescope. Each successive model of the universe has been shaped, and eventually broken, by the honest limits of the instrument in use at the time. The paradigm of a fixed and finite heaven gave way to the paradigm of measurable stellar distances, which gave way in turn to the paradigm of a universe filled with galaxies, which gave way only recently to the paradigm of a cosmos whose very fabric is stretching outward at an accelerating rate. At no point in this progression did the previous model announce its own inadequacy. It was, in every case, the arrival of a better instrument that made the older certainties untenable. What follows is a chronicle of that long unfolding. It begins with a single measurement made in the 1830s, and it ends in a present whose deepest features remain unexplained. Along the way, three great paradigms rise and are, in their turn, absorbed. What is preserved from each of them, and what is quietly discarded, is the substance of the story. The prelude to that first measurement had lasted for more than 2,000 years. The geometry required to determine the distance to a star had been understood since antiquity. If an object could be observed from two different positions along a known baseline, and if the angle by which its apparent position shifted between those two observations could be measured with sufficient precision, then the distance to that object could be calculated by trigonometry alone. Surveyors on Earth had used this principle for centuries to map coastlines and to determine the heights of mountains. The difficulty in applying it to the stars was not conceptual, it was mechanical. The baseline available for stellar observation, even at its most generous, was the diameter of the Earth's orbit around the Sun, and the shifts to be measured against that baseline were so vanishingly small that no instrument built before the 19th century had been capable of detecting them. Astronomers had tried. Tycho Brahe in the 16th century had searched for stellar parallax and had found none, which he had taken, quite reasonably given the precision of his sights, as evidence that the Earth did not move. James Bradley in the 1720s had failed to detect parallax as well, though in the course of his failure, he had discovered the aberration of starlight, which had at least confirmed that the Earth was in motion. For more than a century after Bradley, the search continued, and for more than a century it produced nothing but upper bounds. The stars, it seemed, were too far away for the instruments to reach. The instrument that finally reached them was a device called the heliometer, refined into an object of astonishing precision by the Bavarian optician Joseph von Fraunhofer. A heliometer is, in essence, a refracting telescope whose objective lens has been sawn cleanly in half, with each half mounted so that it can be shifted laterally against the other. By adjusting the two halves so that the images they produced overlapped precisely, an observer could measure very small angular separations in the sky with a repeatability that no ordinary telescope could match. Fraunhofer's workshop produced only a handful of these instruments, but each one was, for its time, without equal. One of them was delivered, in the 1820s, to the observatory at Königsberg, which was then the easternmost outpost of Prussian science. The director of that observatory was Friedrich Wilhelm Bessel. a self-taught mathematician who had come to astronomy through a merchant apprenticeship and who had, by the age of 30, already established himself as the most careful positional astronomer in Europe. Bessel had spent years building a catalog of stellar positions of unprecedented accuracy. He knew, better than almost anyone alive, how demanding the search for parallax would be, and he had waited to attempt it until the instrument in his possession was equal to the task. He chose his target with care. The star he selected, known then as 61 Cygni, was not remarkable in brightness. It was, in fact, rather dim, but it displayed an unusually large proper motion across the sky, which suggested that it was, by stellar standards, close. Bessel reasoned that if any star could be reached by parallax, this one would be among the first. Beginning in the summer of 1837, he observed 61 Cygni night after night, comparing its position against two much fainter background stars that lay conveniently near it on the sky. He continued this work through the seasons, allowing the Earth to carry his observatory around its orbit, and he recorded, with the heliometer, the minute shifts in the star's apparent position as the geometry of the observation slowly changed. In the autumn of 1838, he published the result. The parallax of 61 Cygni was about 1/3 of an arcsecond, an angle roughly equivalent to the width of a coin seen from a distance of several kilometers. From that angle, applying the trigonometry that had waited for 2 millennia, he calculated the star's distance to be approximately 10.5 light-years. Bessel did not use that unit, of course. He gave the distance in units of the Earth's orbital radius, and the number he reported, close to 650,000 of them, was staggering by any measure his contemporaries could apply. The announcement was received with a mixture of astonishment and quiet vindication. Within a matter of months, the Scottish astronomer Thomas Henderson, working from an observatory at the Cape of Good Hope, published his own measurement of the parallax of Alpha Centauri, which turned out to be even closer. Not long after, Friedrich Georg Wilhelm Struve, working in what is now Estonia, produced a parallax for Vega. 3 independent measurements from 3 separate observatories, using variations of the same technique, confirmed one another. The method worked. Space had, at last, been given depth. What this paradigm preserved from everything that had come before it was the ancient trust in geometry. The Greeks had proven, long before, that triangles could measure the unreachable. Bessel and his contemporaries had done nothing more than apply that proof to a longer baseline than anyone had previously dared. What the paradigm discarded, quietly but permanently, was the notion that the stars occupied a common surface. They did not. They lay at wildly different distances, and those distances could be numbered. And yet, even in the moment of its triumph, the new paradigm carried within it the seed of its own inadequacy. Parallax, for all its elegance, worked only for the very nearest stars. The angles involved shrank in direct proportion to distance, and by the time an observer attempted to apply the method to a star even a few hundred light-years away, the parallax became smaller than the observational error of the instrument itself. There was no way, using this technique, to reach the middle distances of the galaxy, let alone anything beyond it. The mountain was in Southern California, and the century was the 20th. When the Great Reflecting Telescope at Mount Wilson was completed in 1917, its primary mirror measured 100 inches across, and it gathered more light than any instrument that had ever been pointed at the sky. The heliometer had served the previous paradigm faithfully by measuring angles with unmatched precision, but the new questions before astronomy were no longer questions of angle, they were questions of light itself. To reach beyond the local neighborhood of stars, an instrument would need to gather photons that had traveled for hundreds of thousands and eventually millions of years, and to concentrate that faint accumulated glow into an image bright enough to be studied. The reflector, with its enormous silvered mirror, was the tool that made such gathering possible, and the mountain on which it stood had been chosen because the air above it was steadier and clearer than the air above almost any other observatory in the world. Yet even the finest instrument is inert without a method, and the method that would unlock the middle and far distances of the cosmos had, by a quiet historical accident, already been prepared. It had been prepared in Cambridge, Massachusetts, some years before the reflector at Mount Wilson was even planned, by a woman whose employment title at the Harvard College Observatory was that of a computer. Her name was Henrietta Swan Leavitt, and her assigned task was the tedious cataloging of photographic plates taken of the small Magellanic Cloud, a hazy patch of sky visible from the southern hemisphere. She was to measure the brightness of the stars recorded on those plates and to note which of them varied over time. In the course of that work, between 1908 and 1912, she noticed a pattern that no one had noticed before. Among the variable stars she was cataloging was a particular class known as Cepheids, so named because the first of them had been identified in the constellation Cepheus. These stars did not merely brighten and dim at random. They pulsed with a strict regularity, and the length of each pulse, from one maximum of brightness to the next, was tied with unnerving reliability to the star's intrinsic luminosity. A Cepheid that took 3 days to complete its cycle was, invariably, less luminous than one that took 30, because all of the Cepheids she was studying lay within the same small cloud. They were all at approximately the same distance from Earth, and the differences in their apparent brightness therefore reflected genuine differences in their true light output rather than differences in how far away they lay. The consequence of this observation was extraordinary, though it was not immediately recognized as such by more than a handful of her contemporaries. If the period of a Cepheid's pulse revealed its true luminosity, then any Cepheid seen anywhere in the sky could be calibrated. The observer needed only to time the pulse, deduce the intrinsic brightness that the pulse implied, and then compare that intrinsic brightness to the apparent brightness recorded on the photographic plate. The ratio between the two yielded a distance. And unlike parallax, which failed beyond a few hundred light-years, this method would work as long as the Cepheid could still be individually resolved as a point of light. The reach of the technique was limited not by geometry, but by the light-gathering power of the telescope. Leavitt was never permitted to take the next step herself. She was a salaried assistant in an era that did not credit such workers with discoveries, and by the time the broader implications of her law were understood, her health had already begun to fail. She died in 1921 at the age of 53, without ever having been given the opportunity to apply her own relation to the deepest questions it could answer. Those questions would be answered instead by the astronomers with access to the Great Mirror at Mount Wilson, and foremost among them was Edwin Hubble. Hubble had come to astronomy by an indirect route, through the study of law at Oxford and a brief and unenthusiastic period of teaching, before returning to the science that had drawn him since boyhood. In 1919, he took up a position at Mount Wilson, and within a few years, he had turned the great reflector toward the object that had confounded astronomers for the better part of a century. That object was the Andromeda Nebula, the largest and brightest of the mysterious spirals whose nature had remained, in the parallax era, entirely undetermined. Some astronomers had continued to insist that Andromeda lay within our own system of stars, a swirling cloud of gas among the many others catalogued by earlier observers. Others had suspected that it was something else entirely, a separate island of stars lying at a distance so great that the individual stars within it could not be distinguished. Neither camp had been able to settle the matter, because neither camp had possessed an instrument capable of resolving what Andromeda was actually made of. The 100-inch reflector could. When Hubble turned it toward Andromeda in the autumn of 1923 and took photographic exposures of unprecedented depth, he was able to resolve individual stars within the spiral itself. Among those stars, on a plate taken in October of that year, he identified one that varied in brightness according to the unmistakable rhythm of a Cepheid. He timed its pulse. He calculated its intrinsic luminosity from the relation Leavitt had established. He compared that luminosity to the star's apparent faintness on the plate, and he arrived at a distance so vast that it lay entirely outside any possible interpretation of Andromeda as a member of our own system. The number he calculated was approximately 900,000 light-years. Later refinements would revise it upward to something closer to 2.5 million. But even his initial figure was sufficient to settle the question that had waited so long for an answer. Andromeda was not a nebula within our galaxy. It was a galaxy in its own right, comparable in size and structure to the one that contained us, and it was separated from us by an ocean of empty space larger than anything that had ever been measured. The universe, at a stroke, had multiplied. It was no longer a single system of stars whose outer boundaries could be sketched. It was a scattering of such systems, each one containing billions of stars, and the intervals between them were greater than any of the earlier paradigms had prepared the discipline to imagine. Hubble did not stop there. Through the remainder of the 1920s, he and his collaborators applied the same technique to one spiral after another, building a catalog of galactic distances that stretched further into space with each new plate. And as those distances accumulated, another pattern began to emerge, one that had been half suspected in the earlier work of Vesto Slipher at the Lowell Observatory, but had never been placed within a coherent framework. The light from these distant galaxies, when passed through a spectrograph, was shifted toward the red end of the spectrum. The features in each spectrum that ought to have appeared at specific wavelengths were displaced, uniformly and systematically, toward longer wavelengths. And the amount of that shift, when compared against the distance to the galaxy that produced it, obeyed a startlingly simple rule. The further away a galaxy lay, the greater the redshift in its light. The relationship was linear, and it admitted only one straightforward interpretation. The galaxies were receding from us, and the speed of their recession was directly proportional to their distance. This relation, published by Hubble in 1929, was the second great result of the era, and it altered the discipline more profoundly even than the first. A universe of many galaxies had been startling enough. A universe of many galaxies all moving apart from one another was something else altogether. It implied, when the geometry was traced backward, that all of these systems had once been closer together. It implied that the cosmos was not a stable arrangement of objects moving within a fixed space, but a dynamic structure whose very extent was changing with time. Georges Lemaitre, working independently in Belgium, had arrived at the same conclusion by a different route, and had already suggested that the universe might have begun in a compact and dense initial state. Hubble's data gave that suggestion an empirical foundation. The expansion was real, and it could be measured. Those limits were exposed by an instrument that no longer sat on any mountain. In April of 1990, a reflecting telescope with a primary mirror of just under 8 feet across was carried into low orbit aboard the Space Shuttle Discovery and released to circle the Earth roughly once every 95 minutes. Its position above the atmosphere gave it something no ground-based instrument had ever possessed, which was a view of the sky uncorrupted by the shimmer of terrestrial air. Distant supernovae that would have been smeared into ambiguity when photographed from the surface could now be recorded with a sharpness that made their peak brightness measurable to within a few percent. The mirror itself, when first deployed, had been ground to the wrong curvature by a fault in its manufacture, and for the first 3 years of the instrument's life, its images were softer than had been promised. A servicing mission in December of 1993 installed a corrective optical assembly that restored the design intent, and from that moment onward, the orbiting telescope became the most consequential astronomical instrument of the late 20th century. The work it enabled was carried forward by 2 teams of astronomers, working in parallel and, at times, in quiet competition. The first, based largely at the Lawrence Berkeley National Laboratory in California and led by Saul Perlmutter, called itself the Supernova Cosmology Project. The second, a looser international collaboration led by Brian Schmidt of the Australian National University and Adam Rees of what would become the Space Telescope Science Institute, called itself the High Z Supernova Search Team. Both had set themselves the same task. They intended to observe Type 1a supernovae at distances so vast that the light from those explosions had been traveling for the greater part of the age of the universe. By comparing the apparent brightness of these very distant explosions against the apparent brightness of similar explosions at closer distances, they hoped to measure not merely the rate of the expansion, but the way in which that rate had changed over cosmic time. The measurement, both teams understood, would settle a long-standing question. If the expansion of the universe had been slowing under the collective gravity of everything within it, as nearly every cosmologist of the 20th century had assumed, then the most distant supernovae ought to appear slightly brighter than a constant expansion would predict, because the universe, when they exploded, had been expanding faster than it was now, and the light from them had therefore had less distance to travel than a naive calculation would suggest. The teams began their observations expecting to measure the degree of that slowing. They expected to argue about the numerical value of the deceleration. They did not expect to argue about its sign. In the summer and autumn of 1998, both teams arrived, independently, at the same result. The distant supernovae were not brighter than a constant expansion would predict. They were fainter. The light from them had traveled further than the previous paradigm would have permitted, which meant that the expansion of the universe, over the billions of years since those explosions had occurred, had not been slowing at all. It had been speeding up. The rate at which galaxies were receding from one another was greater today than it had been in the deep past, and the difference was not marginal. It was unmistakable, and it was present in both datasets, obtained by different observers using different pipelines and analyzed independently. The announcement, made in a series of papers through the end of 1998 and into the following year, was received across the discipline with a wariness that reflected its magnitude. An accelerating expansion could not be produced by any of the ingredients that cosmology had cataloged to that point. Ordinary matter, dark matter, radiation, and neutrinos all exerted a gravitational pull that could only slow an expansion, never hasten it. For the observations to be correct, the universe had to contain something else, something that filled space uniformly and exerted a pressure that pushed outward rather than pulling inward. Within a few years, the name that had been given to this something had become standard. It was called dark energy, though the name reflected an absence of understanding rather than any positive knowledge of what it was. It was dark in the sense that it emitted no light and could not be seen. It was energy in the sense that it possessed the effects of energy, in particular, a gravitational influence that could be detected only through its consequences. Subsequent measurements refined the picture without resolving the mystery. Observations of the cosmic microwave background, the faint remnant glow of the hot, dense state from which the universe had emerged, were carried out by satellites called COBE, launched in 1989, then WMAP, launched in 2001, and finally Planck, launched in 2009. Each of these instruments measured the temperature of the background radiation across the entire sky with increasing precision, and each produced maps of the tiny variations in that temperature from one direction to another. Those variations carried within them a record of the composition of the early universe, and when the measurements were combined with the supernova data, they yielded an accounting of everything that filled the cosmos. The result was startling in a way that only accumulation can be. Ordinary matter, the substance of stars and planets and every atom that had ever been touched or cataloged, accounted for less than 5% of the total. Dark matter, which had been inferred decades earlier from the rotation of galaxies and the motions of clusters, accounted for roughly 27%. The remainder, close to 68%, was dark energy. The universe, in its dominant composition, was made of a substance whose only known property was that it pushed space apart. The consequences of this accounting for the shape and future of the cosmos were substantial. Measurements of the observable universe, the region from which light has had time to reach us since the beginning, placed its current diameter at approximately 93 billion light-years. This figure was, at first, a source of some confusion, because the age of the universe was known to be only about 13.8 billion years, and no signal could have traveled further than that in the time available. The resolution lay in the expansion itself. Space had grown while the light was crossing it, and the sources that had emitted the most ancient photons visible today had, in the intervening time, been carried by that expansion to distances far greater than the raw travel time of the light would suggest. Beyond the observable region, an unknown volume of universe extends further still, and the accelerating expansion ensures that much of it lies permanently beyond reach. Not because the galaxies within it are moving away in any local sense, but because space itself is being added between us and them at a rate sufficient to outpace any signal we might send or receive. Distant galaxies that are visible today will, in the far future, slip beyond the cosmic horizon and vanish from view, not by dimming into invisibility, but by being separated from us by a widening ocean of new space. What the paradigm has come to recognize, and what earlier eras had no means of appreciating, is that the largest thing that has ever existed is not a distant object catalogued at the edge of the reachable sky. It is the fabric of space itself, and it is present in every gap between every particle in every room. The expansion does not occur somewhere far away. It occurs everywhere at once, more perceptibly across the vast intervals between galaxies, less perceptibly within the bound systems that gravity has stitched together, but never absent from any location. What separates the galaxies also passes through the observer who watches them. For those willing to continue this chronicle as it unfolds, and to sit with the long arcs by which these ideas continue to change, the invitation to follow along stands open, and further considerations of this kind are gathered under the name of this channel. The reflection that remains is a modest one. Each earlier paradigm had believed itself to be looking at the whole of the sky. The astronomers who applied geometry to 61 Cygni had believed they had reached the depth of space. The astronomers who resolved Cepheids in Andromeda had believed they had catalogued the true extent of the universe. The astronomers who charted the recession of the galaxies had believed they had described the manner of its expansion. Each had been right in what they measured, and each had been mistaken in supposing that what they measured was all there was. The instruments they possessed had reached as far as those instruments were capable of reaching, and beyond that horizon lay assumptions rather than knowledge. The current paradigm, in which 2/3 of everything is a substance whose nature remains entirely unexplained, is unlikely to be an exception to that pattern. Somewhere, on some mountain or in some orbit not yet planned, the next instrument is already being sketched on paper, and the chronicle it will extend has not yet been written.